page 2. The surface area increased, right, as we went out to bigger and bigger radii. The electric field dropped off, but the area increases as r squared, E decreases as r squared, right? It drops off as r squared. So those two effects can't, when you multiply them together, you get the same flux every time. And that's what's happening here. We have a small surface area where the electric field is close in, and where the electric field is weaker, we have a bigger surface area. Maybe it's more obvious if I draw it like this. And what ends up happening is the negative flux and the positive flux cancel each other out. Okay? Good question. So, is it consistent with lesson 1? The total electric flux into or out of an enclosed surface is proportional to the charge inside. Here we've got a positive charge, we've got positive flux. Here we've got no charge, the flux is 0, and the positive is greater than 0. So I think we're consistent now. Okay? Next one. Compare the magnitudes of Q1 and Q2 using these two drawings. Of Q1 and Q2, compare. Because the same number of lines originate or terminate on them. How do the signs compare? Right. Which one's positive? Okay. And what are we doing? Compare the magnitude of the flux into or out of the surfaces. Same. We agree? The signs. Opposite, because they are proportional to the charge inside. So flux through 1 is going to be positive, greater than 0. Flux through 2 is going to be less than 0. Okay? Ready to introduce Gauss's law. So you're probably asking yourself, why flux? Why is this so important? What am I going to do with flux? When's the next time I'm going to use flux? The answer is it's not that important. The next time you're going to use it is on the exam. And after that, probably never. But why are we doing it? Because it helps us get the electric field, right? We don't care about flux. But it's a tool that we will use, again, to get the electric field. That's the thing we care about. We care about the electric field. So if there's a way where we can get the flux to help us find the electric field easily, then it's a good tool. And if it doesn't help us easily find the electric field, then it's not a good tool. Turns out that there are some cases where there's nice symmetry to the problem. Spherically symmetric case is one of them. Cylindrical symmetry is another one. So when we have nice symmetry, this works beautifully in finding the electric field. And that's when we use flux. Other than that, we don't care about it really. We will use magnetic flux is important. So learning about flux is good for that. And it's, like I said, in a few cases, it helps us to find the electric field really easily. And so that's why we're going through this. This is Gauss's law. This is the flux. That's a fancy way of writing the flux. Let me just write it as flux. I'll put it over here. Flux through a closed surface equals Q in over epsilon naught. And so what does this mean? It means that that's what we've been saying all along. The flux is proportional to the charge inside. Flux is proportional to Q in, the charge inside our surface. And this is a constant, the proportionality constant, so we can put an equal sign in there. Epsilon naught. You can look it up in the front of your textbook or in the back of your textbook. This integral is just a fancy way of determining. It's the electric field integrated over the area. And if the electric field is perpendicular to the area and constant over the area, then what does this become? It just becomes E times A. So in the cases that we're going to be dealing with, because we don't integrate in this class, the cases that we're going to deal with, this is basically going to be the electric field multiplied by the area, or maybe the trickiest case, the electric field multiplied by the area multiplied by cosine theta. Okay, that's what we're going to be using. Instead of the integral of E dot dA, we'll be using E times A times cosine theta. So that's the flux, and it's going to be equal to the charge inside over a constant. So I'll show you in a minute. First, let's just do a little exercise, see if you can figure out what the flux is now, given the charge inside. So let's look at this first case. So we have a plus Q over here, we have a minus Q over there, and they've drawn some surfaces in here labeled 1, 2, 3, and 4. And remember, these surfaces, what's drawn here is just where that spherically shaped surface intersects the plane of the paper. It's really a three-dimensional surface that encloses the charge in case 1, and in case 3 it's off here, it doesn't enclose a charge. In case 2 it encloses the negative charge. So you see how in case 4 it encloses both charges. So you're going to determine the flux through each one. Write it in terms of, they're telling us that that is a plus Q and a minus Q. It's proportional to plus Q. We want to make it an equal sign, though. So we have to put over epsilon naught, right? That constant. So the flux through a closed surface is the Q inside over a constant, epsilon naught. So that's what it is for the flux through surface 1 is just Q over epsilon naught. It encloses a charge of 1Q, right? And through surface 2, you already said it, it's the opposite of that, right? Because this set now encloses a negative Q. So the flux through surface 2 is negative Q over epsilon naught. What's the flux through surface 3? 0, because it doesn't enclose any charge, just like the worksheet we did a minute ago. And how about the flux through surface 4? What do you think? Zero. It's the net charge inside, the Q inside. And we have a plus Q and a minus Q. So the Q in is 0 for surface 4. Okay, you're starting to get a handle on it? Let's do a more interesting one here, see if you understand it. See if you can figure out the flux through those surfaces. Let's do surface 1 first. There's a plus 2Q, there's a plus Q, and there's a minus Q, right? So you add them all up, and you get a plus 2Q over epsilon naught. Just add up all the charge inside. Make sure you retain the sign of the charge. How about surface 2? Minus Q over epsilon naught. You got that? I'll write it as it's a plus Q minus a 2Q minus Q over epsilon naught. Surface 3. positive Q over epsilon naught. There's only one charge inside there, so that's it. Surface 4. Zero. There's no charge inside. So again, using the water faucet analogy, there are no faucets in there, there are no drains in there. So any water that flows in on one side has to flow out on the other side. So the net flux is 0. The only way you can get a net flux is if you have a source or a drain, right? Somewhere the water is coming from or somewhere the water can go to, a source, a faucet, or a drain. A positive charge or a negative charge. And surface 5. There's only one charge inside there. It's negative 2Q over epsilon naught. So let's see how we use this. As I told you, it's really flux. We really don't care about flux so much. What we care about is the fact that flux will link us to the electric field. And how does it do that? It does it here. Flux is equal to EA cosine theta. And what else is flux equal to? Q in over epsilon naught. So that means that EA cosine theta has to equal Q in over epsilon naught. So this is what we're going to use now to figure out the electric field. We already know what it is. What is the electric field from a point charge? What is it? KQ over R squared, right? We already know what it is. Now let's see if we can figure it out using this, what's in the yellow box. That's Gauss's law. So here's our point charge, Q. Let's make it positive. And so our electric field points radially outward. And we're going to draw what we call a Gaussian surface. We want to know what the electric field is right here. And so what are we going to do? We're going to draw a Gaussian surface here. We're going to draw a sphere. That's a sphere. We're going to draw a sphere with the surface at the location where we want to know what the electric field is. So this has a radius of, let's just call it capital R. So what's written in the yellow box here? The electric field times the area times cosine theta has to equal Q in over epsilon naught. So my area vector points outward, right? And my electric field points outward, so I have a cosine of 0 degrees, which is just 1. So I have an electric field times the area. What is the area of a sphere? 4 pi r squared. And so my electric field is, let's bring this to the other side, Q in over 4 pi epsilon naught r squared. So far, so good? So the question is, what is this 1 over 4 pi epsilon naught? Well, it's K. That's the 1 over 4 pi epsilon naught is equal to our constant K that we use in KQ over R squared, right? In K, Q1, Q2 over R squared for the force. This electric constant, K, 8.99 times 10 to the 9th. So what is our electric field equal to? KQ over r squared. And, oh, what is this r? I should put it in here. This is the capital R, right? This is the radius of our Gaussian but that's where we want to know what the electric field is, right? That's the position we want to know the electric field. So it's kq over r squared. And we knew that from earlier. But I'm just showing you that we could get that fairly quickly using Gauss's law. Because there's something we didn't know from earlier. We didn't know the electric field from maybe a solid sphere. We knew a point charge. Well, what if it was a ball, a sphere of charge, uniformly distributed throughout the sphere? Total charge Q. Well, the electric field looks similar, right? It's going to be radially outward. We want to know the electric field over here. We draw our Gaussian surface, a sphere, because we pick the same symmetry. In this case, it's a spherically symmetric charge distribution. We pick a sphere to draw the surface around it because we want every one of these lines to be perpendicular to the surface. Or parallel. That works also. But in this case, spherically symmetric, you pick perpendicular everywhere. You wouldn't draw a cube around this because then every ray has a different angle, right? It becomes a nightmare to try to solve that. You want to pick where the angle is the same for everything. So in this case, what do we get? This is a sphere again, 4 pi r squared. This is just k. Oops. What is that? That's the same as a point charge. It turns out, as long as you have spherical symmetry here, this is a spherically symmetric charge distribution. If you are outside of it, we can view it as if it was a point charge at the center. It looks the same. When you're outside of a spherically symmetric charge distribution, looking at the electric field it's producing, it looks the same as if a point charge was at the center producing that same electric field.